Okay, in this video we'll do an example of a central limit theorem. Alright, you see a problem in question there. You can pause the video now and read the problem. Basically, it talks about the amount of bacteria in raw milk. Okay, so it states that the population mean is 2,510.3. So population mean is 2,510.3. That's per milliliter of milk, with a population standard deviation of 348.7, also per milliliter. Okay, so in this particular dairy, an inspector comes from health department, takes 42 random samples. Okay, all right, so that is going to be our K. Okay, some books use letter N, lowercase n or capital N, but I use letter K here. Right, and what we want to know is that if the acceptable count or level is between 2400 and 2650. So if the level is outside of this, then the milk is not acceptable to be sold. Okay, so question is, what is the probability that the mean of 42? Okay, so they're going to take this 42 samples, put through some type of machine, and measures the bacteria count for each of the 42 samples and takes the mean of the 42 is within the acceptable count. And if you notice that since K is larger than 30, we do not need to worry whether we have a normal distribution or not. Alright, so let's go. So this problem can be rewritten in mathematical form as, what is the probability P that the mean of 42, the low end is for 2400, and I use the notation mean of 42 samples is between 2400 and 2650. Alright, so that's the problem in question. And what we need to do is convert these to our z values. Okay, and it's pretty much a similar computation. Okay, so let me move a little bit to the side here and do our, what is the z of 2400? Okay, and the computation is done by 2400 minus the population mean of 2510.3 divided by standard deviation 348.7 over, remember the formula is square root of that K42. Okay, this is pretty messy to do in the calculator, so I introduced a little simpler way to do, and that is pretty much the same at the top, except now this square root of 42 is going to be a multiplier in the numerator, and the denominator is going to be our good old standard deviation. Again, this is much easier to do in your calculator than the previous one. Okay, so let's do that in the calculator. So I'm going to put that in the calculator. Alright. Okay, and before I begin, I want to let you know that I utilize my memory function quite a bit, especially here when we know we will be entering this population mean of 2510.3 and standard deviation of 348.7. We're going to have to enter that at least twice because we do need to compute the z for each of these x mean values. So what I'm going to do is I'm using this old calculator and I'm going to enter 2510.3. Okay, you see that's our population mean. Okay, and I'm going to store that in the memory. Okay, now this particular calculator, all I need to do is press STO, press that, and press 1. Okay, what that means is that value has gone into my memory cell 1. Okay, and I'm going to enter this standard deviation of 348.7. So let me clear that. 348.7. That's the standard deviation. I'm going to store that in memory cell number 2. So press STO 2. Okay, let me clear this and just verify that I did enter these two values into correct memory cell. To bring it back, you press RCL, stands for recall. RCL 1, as you can see, my population mean comes back. RCL 2, and my population standard deviation comes back. Okay, all right, so now I verified that each of the number is stored in the memory. Let's go, and that should speed up my computation. Okay, let me put it here to be better. Okay, so first 2400, 2400 minus the mean, which is in store memory cell 1. So all I have to do is recall 1. I usually press equal sign, multiply by square root of 42 times 42 square root, okay, equals, so that value of negative 714.8 and some is my numerator, divided by, this 348.7 is in recall 2, equals, and there I have my z value of, I'm going to round that off to about negative 2.05, okay, about approximately equal to. Okay, so that's my first z value, and let me write that down as my negative 2.05. Okay, I'm going to do a similar thing for my next z, which should be my z of 2650. Okay, very similar to this. So that should be 2650 minus 2510.3, whole thing multiplied by square root of 42 divided by my standard deviation. All right, let's do that in the calculator. 2650 minus, recall 1, equals, you can see that very clearly, times 42 square root, equals, and divided by recall 2, equals, and I'm getting the result of about 2. Okay, be careful rounding this off. It should be 2.60. Okay, we got to round up, and because after the 9, the decimal 6 is clearly larger than 5, so that's going to be about 2.60. Okay, all right, so there we have our two z values. One is positive, one is negative. Okay, before I proceed on, let me just do a quick verifying. Okay, obviously this is negative, and that makes sense because this value 2400 was below the mean. The other one, 2650, is positive because 2650 is above the mean. Not only that, look at how far these z values are away from the z value of 0. 2.60 is clearly further away than the negative 2.05. That means, is it true that 2400 is closer to the mean than the 2650 is? Okay, if you do a quick computation, it is. All right, just check this value. This is about 110 units away, whereas these two, they are separated by about 140. Okay, that means this value is farther away from the mean than 2400, meaning the absolute value here of this z value should be larger than this absolute value. Okay, right, that checking technique is important in case you make a little error. All right, so now this is the usual probability computation. If you wish to draw a picture, 0 here, and let's say negative 2.05 and 2.60. Let me exaggerate a little bit here. Okay, I want to know what is this entire area. Okay, and hope you can see that this will be, the whole thing is the area of 2.05 plus here will be simply just adding the two areas. We're not going to subtract anything, well, there's no 0.5 coming into play. Okay, hope you can see why I'm adding these two areas. Okay, so go to our good old table. Okay, 2.05 is, what's 2.05? 2.05, it looks giving me 0.4698. I'm sorry, 4798. Sorry. Okay, 0.4798 plus 2.60. That should be pretty quick. 2.60 should just be 0.4953. 0.4953. Okay. So adding these two, 0.4798 plus 0.4953 equals, I'm getting 0.9751, or if you wish you can write that as about 97.51%. Okay, and this means there is about 97.51% chance that the entire batch of this didn't really tell you how many milk was produced. There's not much probability that it is within the acceptable region. What this does not say is that 97.51% of the whole batch is acceptable. No, that doesn't say that. Okay, that is a totally different type of problem. Okay, all right, so that's the answer.